Well, once again, let me welcome everyone to our presentation. This is RPX Technologies, the makers of DynaVibe, and we have gathered together today to talk about the top 3 vibration causes. And vibration is never a good thing when we're talking about aircraft. And so Matthew Dock, who is our co-founder and also someone who has a master's in mechanical engineering, is going to take us through our presentation today. Before he does that, and before I turn things over to Matt, what I'd like to do is just tell you we would love to have your questions. So you should see on your console an area where you can enter questions. So please feel free to enter your questions anytime during our presentation. I'll watch for those. What we'll do is we'll wait till Matt is finished. So towards the end, we'll get to your questions if you have some you'd like to ask us. Again, our presenter today is Matt Dock, who is one of our co-founders. Matt has a lot of experience with vibration detection. He owns 3 airplanes himself, 2 of which are experimental. He has a Long Easy and he has a Kit Fox on floats. So he knows all about balancing aircraft propellers and finding vibration. So what I'd like to do without further delay is click in the right place and have Matt begin our presentation.
All right, hopefully everybody can see that. I appreciate that, Jerry. So as Jerry said, my name is Matthew Dock. Work here at RPX, engineer. Kind of starting off, I'm kind of excited about this, showing some of the aircraft we've worked on recently. We've got the Voodoo that's getting ready for the Reno Air Races. We just balanced the Bugatti, which flew recently. Kind of a neat photo there. So we'll go ahead and go through this. We're going to talk about vibration, the effects, the causes of vibration, some terminology, detection, and correction of vibration. And then we'll give some examples and some tips, and then we'll get into some questions. The vibration effects include bearing wear, which is to the 3rd power of load. So an increase in load, say a 10x increase in load, will actually cause a 1000x decrease in bearing life. So this is why a lot of times you'll see the gyros in the panel will go out. Anything with small ball bearings will usually have a much shorter life because of vibration. The other one is sliding wear. So sliding wear varies with load. So a 10x increase in load from vibration will cause a 10x increase in wear rate. That could be significant. Another vibration effect are cowling cracks. Cowling cracks, a lot of times you'll see stop drills where people are trying to stop those cracks. Those cracks are caused by fatigue. So the flexing of that metal, repeated flexing, especially at high frequency, will cause a crack to start, and that crack will propagate, and you try and stop that by putting a stop drill. We actually had an interesting case where the vibration on a Kit Fox was so bad that we actually watched the crack grow in the windscreen. So it can be very expensive to have these cracks propagating because of the vibration. Another issue are exhaust cracks. So this is actually my Cessna 150. It had an exhaust crack develop due to vibration, and that actually pumped exhaust into the fresh air vent, so potentially very dangerous situation. Power flow exhaust, if you buy a power flow exhaust system, they actually require that you have a dynamic balancing procedure done in order to get the extended warranty. And that's because they realize that damage to the exhaust is typically caused by vibration. So another effect is pilot comfort. So we talked about the fatigue on metal, the cowling, the exhaust. It also has fatigue on pilots. So a lot of times we'll have customers ask about, was prop balancing going to make a difference? And it almost always makes a significant difference. And a lot of times people will talk about how they feel it in their fingertips, their toes, their eyes. And from this chart, you can kind of see the frequencies that typically influence different parts of the body. So for us, at let's say 2400 RPM, typical vibration will be around 40 hertz. So you see that in the head, around 27, the eyes, the throat, normally the fingertips and toes. Those are the items that really get impacted by this high frequency vibration coming off the propeller. We'll talk about some of the causes. The first cause, mass imbalance. We've got three major causes. The most significant is almost always mass imbalance, and that's where the center of rotation is not the same as the center of gravity. That basically means there's a mass error in the propeller and the crankshaft. It's in one of the rotating components. A lot of times this will happen as a natural part of manufacturing. It could be installation error, could be due to damage, moisture, corrosion. So there's a number of things that could cause this. It's very difficult to always get the mass to be centered on the center of rotation. And that's a predominant cause. This video, which will probably be hard to see, is a high-speed video that we took to show the very subtle variation that causes a significant vibration. This spinner is actually out of balance, and the spinner is actually pushing the entire engine around. If you can see it, there's a small dot on the very center of the spinner, and that's actually moving as it causes the engine to vibrate. This customer complained about not being able to fly for more than an hour without his toes going to sleep. And so that was an issue that we were able to resolve by going through the balancing process. This is another example of a mass imbalance. This is actually a manufacturing defect. If you look at the blade, there are two images that are superimposed and they're alternating. And you can see very subtle differences in the shape of the blade. So during manufacturing, in order to get the mass correct, they actually took some material off. So it gives you both a mass error and an aerodynamic error. Another reason for mass error is propeller damage. So this propeller, it's kind of difficult to see, but near the foil tape on part of the blade, there's actually a crack that runs through the blade over to one of the mounting bolts. And so what happens is this blade had a crack develop, and now the mass of the blade is actually out of position. So that crack opens up and that blade shifts slightly. That shows up as a vibration. This is another mass imbalance. You can see the two images superimposed, and it's fairly obvious that if you look at the blade tips, one of them has been filed down. That's fairly typical to repair damage. But what happens is that throws the mass of the blade out of position because there's actually less metal in one tip than the other. Back on mass imbalance, we can see here that there's a moisture corrosion issue. That's typical. It can happen. But again, proper propeller maintenance using advisory circular 20-37 allows us to make those repairs, and then we'll want to rebalance the prop in order to get it smooth again. So the second big cause after mass imbalance is aerodynamic imbalance. So an aerodynamic imbalance is caused by misshape in the blade, an error in blade track. Advisory circular 20-37 has a really good example of how to do blade track. And in this image, you can see, you put a small wood block on the ground or a chair. It's easier if you take the spark plugs out. You rotate the propeller, and you verify that the blade track is the same for each blade. FAA says 1/16 of an inch is the limit. Anything above that, you should have the prop checked by a repair station. A way I like to do it is actually use a small step stool and a wood block on the back of the propeller and then scribe the line. What this does is actually gives you blade track and shows you if there's any pitch error. Sometimes when the blades are installed, they can actually get indexed incorrectly, and there'll be a pitch error. And so that'll show up as an aerodynamic imbalance that can be reduced, but it's very difficult to get rid of a vibration on all RPM ranges if the blade is out of pitch. So another tip is that sometimes we'll have blades that are challenging to balance, and one of the things we like to do is actually measure the blade pitch at multiple locations. EAA has a couple of videos on this that show how to do it. Set up stations along the back of the blade so that you can actually put masking tape at different locations and then measure the pitch at each location. And this allows you to actually profile the blade and to understand what's going on as far as the pitch change versus position. Each one of those blades should be the same. If you have one blade that has a slightly different pitch, that's going to cause a significant vibration. Some of that will be corrected by dynamically balancing, some of it won't. So again, I go back to the aerodynamic imbalance with the blade shape. It's challenging to balance these blades if they are significantly out of balance. I actually had a customer who was flying an AgCat that he had two different models of blades on the same hub. And they were, I walked up to it and they were literally different shapes. So that's going to be very hard to get an adequate balance in a situation like that. So we talked about the mass imbalance, talked about the aerodynamic imbalance. The third is it's complicated. A lot of times with the first two, the mass and the aerodynamic, mass imbalance can almost always be balanced out using an analyzer. Aerodynamic imbalance, those issues can be minimized. And then when it gets complicated is where you need something like a vibration analyzer like the GX2 in order to understand what's going on with the engine. So the residual vibrations are usually related to compression, spark, fuel flow, bearings, intake exhaust variances. So there's kind of a laundry list of things that we go through to verify what the vibration cause is, and we'll talk about some of those in the upcoming slides. So a little bit on terminology. The slides we're getting ready to show talk about vibration on aircraft, and when we talk about that vibration, we're going to be talking about it in terms of inches per second. So that's the velocity of the vibration. So we measure it in acceleration, but because of the speeds that we're operating at, velocity actually works a lot better. And so we display all the data in inches per second, and that's the velocity that that airframe or that engine or that propeller is moving up and down. Something else we're going to talk about are the per ratios. So it's kind of important to kind of get through this little section on what the pers are. So a 1 per vibration means that that vibration occurs once per prop rotation. So if the propeller is spinning at 2400 RPM and the vibration occurs at 2400 RPM, then that's a 1 per vibration. And we know that that is caused by the propeller. A 2 per vibration is something that occurs twice per rotation. And so that would be, say, from a two-bladed propeller. Each blade, as it passes maybe a part of the cowling or a wing, in the case of the long easy, the two blades pass behind the two wings, and so you get 2 thumps per revolution. So something occurs twice per the rotation of the blade. So that'd be a 2 per vibration. You can also have a 3 per if somebody has a 3-bladed propeller. You could have a 3 per, which means there's something occurring 3 times per rotation. Now I kind of skipped over the half per. It's actually one of the most interesting vibrations because it gives us an idea of engine health. It will specifically tell us how well that engine's running. So a half per vibration is something that occurs every other rotation. So for a 4-stroke engine, each cylinder will fire every other rotation. And because it fires every other, it's called a half per. And the half per vibration is significant enough that it's given its own position on our spectral chart. So if you look over in the right-hand corner of this display, you'll see the velocity mode inches per second. There's an H for half per. Anything that shows up in that dashed vertical line under the H is a vibration at half per, which means it happens every other prop rotation. You see the 1, a little bit above 0.2 inches per second. That 1 indicates that that's a propeller vibration. So that's actually a mass error in the prop. It hasn't been balanced yet. You'll see a 2. There's a 2. That's a 2 per. And that's because this is a long easy, and when you fly the long easy, the blade passes behind the wing, and you get a thump thump. You get twice per revolution, you get a vibration. And then you also notice something out between 2 and 3. That's actually a 2.6 per. That's actually the alternator. The drive pulley, the driven pulley on the alternator is actually out of balance, and you can pick up that vibration. So we're able to look at this spectral graph and completely understand what's causing all of the vibrations in that engine. Okay, so we'll go ahead and progress on and take a look at some of this other information. So how do we correct it? We install the equipment, usually as far forward on the engine as possible, right up by the propeller. This engine has a prop extension, so it's as close as we can get is to the starter ring. We then run the engine, and this is the DynaVibe Classic, so this is a straight prop balancer. It's going to give us the magnitude of the vibration and the location of the heavy spot. So we warm the engine up. We use our averaging signal to lock in the RPM and the amount of vibration. This one is 0.88 IPS at 258 degrees. The FAA limit is 1.20. So this 0.88 IPS is 90% of the way to the FAA limit. This is a pretty bad vibration. When you're sitting in the cockpit of this aircraft, you'll get your teeth will chatter a little. You put your head against the windscreen, you get a very significant buzz coming off the airframe. So we've got our 0.88 IPS. It gave us the location of the heavy spot. So what we do after we shut down, we rotate that propeller till it's in line with the phototac. So you'll see the small yellow phototac lined up with the tape. And then after we have it lined up, we simply measure from the accelerometer, which is mounted vertically at the top of the engine, and we go in the direction of rotation, whatever it said on the screen, 258 degrees in this case. So right at the very top is 0 degrees. We go in the direction of rotation, 258 degrees, and that is the heavy spot. So the system tells you where that assembly is heavy. You could remove weight there, but in most cases it's a lot easier to add weight. So we're going to add weight to the opposite side. We start with 50 grams per IPS. So in this case we're going to add at 78 degrees in order to make that correction. We're going to rerun. Normally it takes 2 or 3 runs to get that vibration down. So I think this was after 3 runs, a final reading of 0.06 IPS at 313 degrees. Normally we want to see that below 0.07, and then we'll stop. All of the DynaVibe equipment allows you to go as low as you want. A lot of times it takes some time if you really want to get it to 0. A lot of our Reno racers really want to get that vibration completely eliminated so that at high speed those vibrations are nulled out. So something about vibration correction if you run into problems. We occasionally get calls from customers that say, you know, the system, it's showing odd numbers. The phase angle is changing. What that usually means is that there's a problem. So a lot of times when the balancer doesn't appear to work correctly, you can actually start tearing apart, take the spinner off, inspect the propeller, double check your bolt torque, look for cowling rubs where the engine may be bumping up against the cowling. In every case, there's been a issue with the airframe versus the actual instrumentation. So that really helps give you an idea that this machine's talking to you. It's trying to tell you something. You have to dive in and figure out what's going on. This is another one, vibration correction trouble. This is the customer that was complaining about his feet going to sleep. We actually balanced it quite well at 2400 RPM one time. Pull it back to idle, run it back up, and then it's out of balance again. Pull it back to idle, run it back up, it's out of balance differently. So this is a fiberglass spinner, and this spinner is flexible. And what was happening is the entire spinner assembly was shifting. It was oil canning the spinner backplate. So if the spinner is not balanced, it's very challenging to get a consistent balance job. So what looks like an error with the instrument is actually an error with the way the fiberglass part is made. If you take this spinner off and lay it on a table, it'll roll to a heavy spot. So that's a test that we have a lot of customers do. Hey, pull the spinner off, lay it on a table, and if it rolls to a heavy spot, you got a problem. Because it's going to be very difficult if that spinner has any flexibility to get it to balance. This spinner was so bad, it actually cracked the spinner back plate. I think it was around $1,500 to have this replaced, because once the spinner back plate's cracked, it's really an unserviceable part. So a little bit about vibration correction advanced. So we were kind of talking about things you can do with the Classic. You can balance your prop. It works great for that. 90% of the time, it's a mass error, and a straight prop balancer will do the trick. 10% of the time, it gets more complicated. There's issues with either the engine or airframe interactions, and that's where the GX balancer comes in. The GX2 has an auto balance feature, so it'll normally balance within 2 to 3 runs. It has a true phase measurement, so it's going to tell you exactly where the heavy spot is. It does spectrum analysis, and we'll talk about that. And then it's got total vibe and built-in reporting, so it's going to save all the information as you work through this process. So one of the nice things about the GX2 for me is the auto balance feature. We use this on the Bugatti. It makes it very straightforward. You notice in the lower right corner, it actually has a graphical setup. You tell it, hey, I put the accelerometer here. I put the photo tack in this location. I've got 6 holes where I can add weight. It's rotating counterclockwise. So you basically graphically configure exactly how you want the system to run, and it's going to figure out where to put the weight. It's going to tell you how much weight to put, what bolt to put it on. So it makes it very simple. You put in all the owner information. That's all stored in a HTML report. After you've put all your information in, you're going to see the screen in the upper right corner. So it graphically shows you the polar chart where the heavy spot's at. It's going to show you the RPM up in the upper right corner, and it's going to give you the IPS and phase. Once you hit that accept button, it takes you to the split weight data page that shows you the vibration, the solution, and the split weight, and how much weight to put on which bolts. So it makes it very straightforward. We did an Antonov AN2 yesterday, and it actually balanced in 2 runs. We ran it once, we added the weight to the blade, ran it again, it was 0.05 IPS, and we're done. So this is a very powerful capability to have it just tell you exactly how much weight to put on. The GX2 comes with a scale, so you add that amount of weight and you're done. Okay, so that's the auto balance feature. I'm an engineer, so unfortunately I'm kind of interested in the spectral data. So the spectral data is what allows you to really understand what exactly is happening to that engine. So this is a long easy. We saw this earlier. It's got a 1 per vibration from the propeller. It's got a 2 per vibration from the propeller going through the wake of the wing, and then a 2.6 from the alternator. So we'll just look at a couple more of these spectral charts. So the upper graph, you see that the H, the half per, is almost non-existent, and the 1 is the prop imbalance. So if you look at the lower chart, you'll see that the prop imbalance is about 0.2 IPS. That's the 1. It's fairly small. But you'll notice that the H, the half per, is at 1 IPS. And that tells us there's something wrong with one of the cylinders. So I was actually doing a long cross country coming back from the west, back into Oklahoma here, and picked up a little bit of a vibration. I hooked the analyzer up. I saw this half per and realized there's something wrong with one of the cylinders. So I did a compression check. All the compressions were good. I pulled all the plugs, cleaned them, put them back into service. The plugs were fine. Mag check was fine. So it actually took a little bit. I actually had a loose intake hose. It was actually had a little bit of a crack in it, so I had to replace all the intake boots. But I didn't have to wonder, do I really have a problem, or was I just thinking there's a problem? I can actually look at the vibe data and go, no, I know there's something wrong because this half per vibration should not be here. This is off of a half VW. There was a lot of talk online about the half VW experimental engines having a very bad natural vibration. So we were interested in this and went up to B-Light in Kansas and hooked up the DynaVibe GX2 and took a vibe survey. And the first thing we saw in the upper right graph was that large 1 per vibration. So that's 0.7, 0.8 IPS, and everything else is fairly low, 0.2. So we knew that it was probably just a prop imbalance. It's a really light airframe. The customer was complaining that there's a lot of panel shake, there's a lot of vibration going on, and we balanced the prop using the auto balance feature, and then we have the spectra in the lower right. And so you can see that 1 per vibration is completely gone. So that prop is now balanced. The customer said he can read all the gauges. The buzz is gone from the panel. He doesn't feel anything in the rudder pedals. What was interesting about this is because the half VW engine, the 2 pistons are offset a little bit, it makes what's called a rocking couple. So the engine tries to move as it's spinning. And in order to fix that, they put a plate up on the prop flange to offset that rocking couple. And it looks like they had overestimated how much of the rocking couple plate they needed, and we were actually counteracting that rocking couple. All right, the next one. This is a Kit Fox 3. It's got a Rotax 582. And some of the interesting things here, you can see again, the prop imbalance is about a 0.3, so it needs the prop balanced. And it has a 3 per. So this has a 3-to-1 gearbox, and that's actually the crank out of balance. So you can see the crank speed vibration. And because this is a geared engine, the crank is running at 3 times the propeller. And then you'll notice in the lower graph, if you inject a little bit of fuel and cause the engine to stumble some, you'll see that there is a half per crank at 1.5. So you can actually see that this engine's running good or running rough based on the difference in those 2 spectral charts. This is a neat one. This is a Widgeon, so it's a pair of geared engines. We looked at the left engine first. This had already been balanced using a straight prop balancer. But when we looked at it using the GX2, we saw that there were a lot of other vibrations in the engine other than just the prop. So on the left engine, we see a half per crank at a little between the half and the 1, because this is a geared engine. we see the half per crank, and at the crank speed between 1 and 2, there's also a large vibration. So the half per crank means there's something wrong with one cylinder. So we did a compression check. We found one cylinder was a little low. We bore scoped it and found a burn exhaust valve. So, nobody wants to have to pull a cylinder, but using the vibration data, we could tell, hey, there's something wrong. Let's figure out what it is. We were able to pull that engine or pull that cylinder out of service prior to losing an exhaust valve. We also noticed on the right engine that he had a 1.5 times the crank. And for a 6-cylinder engine, that's normally related to magneto. He did an in-flight Lena Peak mag check and was able to determine that he did, in fact, have a bad mag, had that rebuilt, and now this aircraft's running smooth. This is another one. This is a Piper 0540. This was down in southern Texas near the border, near the coast. And you can see a large half per 1 IPS. We weren't able to identify which cylinder it was, but based on the vibration, we knew there was something wrong with the engine. And after inspection, we found that the cam had corroded to the point that there was a lot of spalling and damage, and had to replace the cam, unfortunately. But we were able to take this engine out of service prior to in-flight failure. So a little bit about total vibe. So in addition to the spectra, there's a function called total vibe that some of the prop manufacturers like. This allows us to vary the engine RPM from idle to full speed, and it records the vibration magnitude as you change RPM. So it plots out resonance points. So if you look at this particular example, there's a couple of large spikes, one around 1800 RPM, one around 2600 RPM, and those are airframe resonances. So as you pass through an area where the system, the airframe likes to shake, you'll pick up these spikes in the total vibe spectra. A little bit about Rotax. I'm not sure how many of our attendees have Rotax engines, but this kind of shows the capabilities of the GX2. We had some fairly high-profile customers that were having some vibration problems. We go out, we hook up the equipment. For the Rotax, we actually use both accelerometers. The GX2 does come with 2. So we use both accelerometers, one mounted up as close to the propeller as we can get it, as we normally would install it. And then the other one we actually put on the right side of the engine. And what's nice about that is we can record the torsional vibration, the twist of the engine, using that second accelerometer. So a few things that we can see with that. Looking at this particular engine, there's a very small propeller imbalance. It's less than 0.2. It's pretty smooth. There is a fairly small 1.2. So that is the half per crank. So the crank on this is spinning at 2.4 times the propeller. The half per crank is at 1.2, and that's what's going to tell us if there's a cylinder issue. And in this case, it was pretty good. It was 1.2 of 0.3 IPS. The carbs do need balance, but it's pretty good so far. Now this other engine reveals a 2 per vibration. So there is a 2.4 per vibration, and that's actually caused by the front to back cylinder variation on the Rotax engines. If anybody's looked closely at a 912, the intakes are different lengths. So there's a short intake and a long intake on each side of the engine. And at mid speed, at mid RPM range, the two cylinders start competing for airflow, and the front cylinders usually run richer, and you wind up getting this front to back variation in airflow, and that causes a vibration at 2.4 per prop speed. Now this also has a 2 per, and we were able to show that that's related to the gearbox torque. So the torque in the slipper clutch that torque value causes, if it's too tight or too loose, you wind up getting this 2 per vibration. So that can be an issue. This is an animation of a different Rotax. Customer's been fighting for years trying to figure out what's going on. And using the GX2, you can actually see that it's not just one problem, it's 2 problems. There are 2 vibrations. So if you look at the 1 per vibration as it moves from left to right, the 1 per initially starts off small and grows as the RPM increases. And that's very typical of a propeller imbalance. So the propeller on this aircraft's very far out of balance. So it's 1 IPS. It's almost to the FAA limit. The other vibration at 1.2 is the carb imbalance. So when that 1 is below 1200 RPM, you'll see a very large 1.2 vibration. What that means is the engine's running rough because the carb balance initially, and as the RPM goes up, you actually see the carb imbalance go away, but the propeller gets worse. So even though the customer perceives a vibration the whole time, it's actually 2 vibrations that are changing from low RPM to high RPM. So that's something you really can't see unless you have a vibration analyzer that'll show you the spectra and how it's changing as the engine is changing. A couple of tips. So we draw a lot from FAA Advisory Circular 2037. That's the FAA Advisory Circular on Propeller Maintenance. It talks about things you can do, things you can't do. For certified aircraft, you have to be an appropriately rated mechanic to do propeller balancing. It talks about removing the tape when you're done. So it's really a good set of information for anyone ready to do propeller maintenance. Another tip, bolt torque. I've been bitten by this. You need to be torquing the bolts on wooden propellers every 25 hours or when changing environment. We talked about the 1.2 IPS that requires static rebalance. So if you do see a 1.2 IPS, that's kind of the threshold of I need to take this off, send it to a repair station, and have it statically balanced. Because if it's above 1.2, there's probably something wrong with the static balance. Crank runout. So very small variation in crank runout can really cause a lot of vibration. Crank runout is not terrible if it's already been inspected. There are call-outs for the allowable crank runout, but it can cause a significant vibration. A couple other problems. We talked about fiberglass spinners, but there's also an issue with fiberglass backplates. Those fiberglass backplates will creep over time and reduce bolt torque, and then the prop will start chattering. Normally you'll bust a prop bolt and then the whole prop comes off. So anything that allows compliance, anything that allows a loss of bolt torque or compression on that propeller is a significant safety issue. Unbalanced spinners can cause a lot of problems. We see that a lot. The spinner, because it's out there flexible, if it can move at all, then it'll be very hard to balance because it'll be changing all the time. And then blade pitch. We do see, especially with some of the ground adjustable blades, that you get a difference in blade pitch, and that will cause a problem. So we'll talk just a little bit about helicopters. I really only have 2 slides on helicopters. We'll talk about that. One of the things we're coming out with is what's called the DynaTrack, which is a blade tracker for helicopters, so that you can actually see the height of those blades, and it gets rid of this condition where you see a gentleman with a stick and a ball of grease and jam that into the rotor blade. That's kind of the old style of doing it. So we're going to have some accessories for the GX2 that'll help with this. The next slide here is showing the optical tracker along with the GX2's already has 2 accelerometers, so we can set it up to do lateral and vertical vibration. And with the tracker, that's a full rotorcraft solution. So the last slide I have is just kind of it shows the equipment DynaVibe Classics 1495. That's a prop balancer. It's going to balance whatever it sees with that piece of tape. So prop, it'll do a helicopter rotor, it'll do a tail rotor, but it only balances one speed. The GX2, just under 4,000, 39.95. It has the auto balance, the spectra, the total vibe, the two accelerometers, and we see it as a platform for accessories. So we talked about the Dynatrack. We're coming out with a high-speed sensor for doing jet engines. We've got a strobe interface that's coming out. So that's really a platform that's going to be growing in the future. It's got an SD card in it, so it saves all of its data and allows you to generate PDFs, and you can provide that to your customers. For people that are doing this as a business, the GX2 really allows you to document what you've done and the improvements you've made, and then you can look at that next year to make sure things haven't changed. It works out really well for that. Jerry, I think that's all I have. If there's any questions.
All right, Matt, thanks. And yes, we do invite your questions. So if you have any, and we do have one already, please feel free to enter those questions. We'll get to them now. And let me also just once again apologize for the technical difficulties we had at the start. Here's what we're going to do. Matt and I will record this webinar again separately and post it to our YouTube channel. And we'll make sure that everyone has the link to that once we get that put up there. So with that, let me get to the question we have so far. And if you think of something you want to ask about, please go ahead and enter your question. So Matt, here's a question we have. And let me just make sure I get this correct. It says, and I'm going to refer to a slide, Matt, if you want to try and navigate back there. It's 2 or maybe 3 slides before the slide of the B light with the half VW. So it's in that neighborhood. So you're pretty close, I think, right there. And so here's the question. In the explanation, you said that the phase angles were arrayed in the direction of rotation. However, our tech people are saying always clockwise. Was that, which was what was shown on the previous slide? Which one is it? So I think there's just a question about which way it's supposed to be. Does that question make sense?
It does. So that's a really good point, and I appreciate that, and we should update this to reflect that. The DynaVibe Classic, so this unit that just shows IPS and angle, always go in the direction of rotation. So if you're using a Classic, you just got to think in your head, direction of rotation. The GX2, because we give it this information, because we tell it what direction the prop is spinning, the GX2 automatically corrects for that, and that is in clockwise direction. So that's a great point, and we should have made that clearer. The Classic is direction of rotation. The GX2 is clockwise. As you can see in the image, lower right corner, it actually has the 0, 30, 60, 90 in the clockwise direction, even though the propeller is spinning counterclockwise. That's part of the reason for the GX2 is to take a lot of the complexity out of it. It's just going to graphically blink a particular bolt that you want to put the weight on. That way it takes a lot of the guesswork out.
Okay, so I appreciate the explanation on that. Hopefully that's helpful. And so now another question, and if you have other questions, please keep entering them. So Matt, you said in the presentation that the most likely cause of vibration is propeller imbalance. That's number one. I think you even said 90% of the time. So what in your experience is the next most likely cause of vibration?
So normally after mass imbalance is an aerodynamic imbalance. So if we balance a prop at cruise RPM, and that's normally what we want to do, we want to balance it at cruise, that fixes both the mass and the aerodynamic imbalance at that RPM. So one of the things I like to do is then pull it back a little bit, pull the RPM down some, take a look at it, and make sure the vibration doesn't get worse. So if it does, that usually means there's an additional aerodynamic imbalance. The other thing I like to do is balance it at cruise RPM And if you have a constant speed propeller, you can then add a little bit of manifold pressure. Go ahead and increase the pitch on those blades. And when you do that, you should not see the vibration get significantly worse. So if you balance with the blades flat, and then you get a vibration as you add pitch, that really indicates you need to look at that blade pitch angle to make sure they're both the same. As you add pitch to both blades, the vibration should not go up. And you can do that using that digital protractor that I showed.
Okay, thank you for that. If you have other questions, again, feel free now to enter them. So here's another question. You said, I think towards the end of your presentation, that if you do reach the FAA limit for vibration, was it 1.2 inches per second, that you need to take the prop off and have it statically balanced. So if you do that, when you get the prop back, does that mean you don't need to dynamically balance it since you sent it off to have it statically balanced?
Well, we always feel like a great static balance is a good starting point. We hear a lot of times, hey, my prop's balanced at the manufacturer and it's not going to need to be dynamically balanced. But one of the things to think about is when you put that propeller on, if it's off by a half of a thousandth of an inch, I mean, unless you have perfect guide pins, you're talking about a 40-pound, 50-pound prop that may be shifted slightly. That very small assembly error can cause 0.6, 0.7, 0.8 IPS. So there can be a significant vibration even with a perfectly balanced, statically balanced prop. There's also issues where the center of gravity, it could be in the middle of the propeller, but one propeller blade could be heavier toward the front of the plane and the other propeller blade is heavier toward the back of the plane. So you put it on a static balancer and it works great. But then as soon as you spin it up, it tries to straighten itself out and you pick up a vibration. So static balance is a great place to start, but you should always have it dynamically balanced before putting it back into service.
Okay, and we have other questions still, so let me hit you up with them. This question is curious about vibrations less than half per. For instance, I'm working on an R22 main rotor and have vibrations that would be, looks like 1/5, 1/20th, etc.
Okay, so if when you say per on a R22, I'm assuming you're talking about balancing the main rotor. If you see something 1/5 or 1/20th of the main rotor, that's more than likely just air turbulence. So even in a lot of our graphs, you might see vibrations less than a half per. And one of the things to remember is that those graphs are screenshots. So the GX2 allows you to take a snapshot of whatever's on the screen. So that's a moment in time. What to look for on those lower frequency vibrations is if they move up and down. So if we're out balancing on a windy day, say 10 knots of wind blowing, that aircraft is going to be kind of rocking around. We see this on a lot of lighter airframes that maybe are cloth covered, or some of the RV series where the metal skin starts popping. When you're really loading that airplane up, especially with fixed pitch prop, the airplane will start dancing around, and that'll show up as a 1/5 per, a 20th. It shows up down in that very bottom range. And so the trick there is to watch it over time, and if it's not a consistent peak, if it's coming and going based on just the turbulence, then you know that that's just an aerodynamic turbulence caused by airflow. So something like a helicopter where the blades are beating against the bubble, the canopy, and it's causing a lot of low frequency rumble, that's probably what that is, that 1/5 to 1/20th.
Okay, and a lot of questions still coming in, Matt. By the way, question was, will we make the slide deck available? We're happy to do that. So sometime after the webinar, we'll send out an email with a slide share link or something so you can have that information. Okay, here's another question for you. Let me scroll through and get to my right place. Okay, here we go. This has to do with the 912. On the 912 engine, how do you add weight, for prop imbalance when there's no spinner or spinner plate, and how are the weights attached?
Yeah, so some of the newer ground adjustable props, it's difficult to find a place to put weight. A lot of times we'll either do it underneath the prop bolts, so you can actually put a larger washer underneath the prop bolts. You have to be careful. You always want to have threads extended through the prop flange so that you've got threads visible. So you may have to actually go with longer prop bolts. Or some of the attachment points, if you're running a Cincinnati that's ground adjustable, the bolts that actually clamp the blade roots, you can put weight underneath there. So if you get outside, if the weight's not in line with the blades, then you probably have to use the prop bolts. A lot of people think, the weight addition is going to be right on top of one of the blades. A lot of times, because of assembly variances, that may not be the case. Like I said, the static imbalance may be great, but just mounting it on that particular engine is going to cause an error.
Okay, and here's still more questions. So this question begins this way: how do we know what a particular vibe signature means or points to? And kind of the follow-up on that is something specific. Would an unbalanced crankshaft have a different signature than an unbalanced camshaft?
Okay, it's a great question. So all of the certified engines, the vibration ratios are available in type certificates. So if you go to the FAA website, look up the type certificate for IO 540. Listed in the type certificate are all the ratios. So it'll tell you what the alternator ratio is, the generator ratio, all of the accessories are listed on that type certificate. So if you see a vibration and you look at that ratio, pull the type certificate up, and you can just look and see which component it is. If you want to have a lot of fun, you can do this with like a P51 engine that has, I think the list was around 20 different ratios for all the accessories, including the blower. The blower has 2 speeds. So really, without that document, it would be very challenging to know which component it was. But if you have that document that shows you the ratios, and that's available in the type certificate, it's a very powerful tool to just pinpoint exactly what the issue is. Regarding the crankshaft and the camshaft does run at a different speed than the crankshaft, runs at half speed. So you would be able to pick out the difference between the crankshaft and the camshaft. The other thing you can do is by mounting one accelerometer on the front of the engine and another accelerometer on the back of the engine, you can actually pinpoint where the imbalance is along the assembly. It's a little more of an advanced feature, but that does allow you to really fine-tune what's going on. Is the imbalance in the prop? Is it in the crank? Is it in the accessory case?
Very good. Okay, still a few more questions to go. I think we're down to about 3. So this question is, for a prop that has been previously dynamically balanced, do you leave previous weights on when doing a new dynamic balance? What's your recommendation there?
So in a situation like that, the way I prefer to do it is to go ahead and run the dynamic balance with the weights. The reason is normally there won't be a huge change in vibration unless the props had a nick or some paint flown through rain. I mean, there are reasons that the balance is going to change. I would use the dynamic balancer with the previous weights, but if it's above 0.1 IPS, I would then pull all the weights off and start fresh. We do that all the time because that's an issue where you want to start from the baseline in order to do the dynamic balance correctly. So, hook it all up, run it with the previous weights. If it's above 0.1 IPS, take all the weights off, start over.
Okay. The next question is this. For the out-of-plane imbalance that you just mentioned, Matt, one blade heavy towards the front, one heavy towards the back, does that still show up as a 1 per vibe? How would the DynaVibe unit describe where to add the mass?
Yeah, that will show up as a 1 per vibration. You do it as a standard prop balance. One of the things that'll happen there is you'll really pick it up using your aft accelerometer. So you would actually set up two accelerometers, one at the front and one at the back. And if it's balancing properly, both the front and back accelerometer should reduce together. And so kind of a telltale problem is you balance the prop, it doesn't seem to balance correctly. You put an accelerometer on the back, and then you'll pick up this issue where you've actually got it what's called a dynamic couple.
And again, on any of these questions, if you want to follow up and get a little bit more information, please contact us. Email address is sales@rpxtech.com. Okay, we're down to the last question, Matt. Here it is. Can you do an actual flight with the balancing equipment hooked up on a certified aircraft?
That's a great question. We get that asked a lot. The equipment's not TSO. It's a torque wrench. It's a tool for doing maintenance. And you wouldn't fly with a torque wrench in flight. Same thing with this equipment. For certified aircraft, it's not FAA approved for in-flight operation. That being said, I've got an experimental Long Easy. I do fly with it as an experimental aircraft. The Long Easy, I only get 2,200 RPM static. I like to fly at 26 and 2,700 RPM in flight. So I get a better balance by doing it with the equipment hooked up in flight. But for certified aircraft, unfortunately, that's not allowed.
Okay, there you go. I hope we were able to get to your question, and we invite you to keep the dialogue going with us after the webinar ends. And so here's how you can do that. Visit our website, www.rpxtech.com. Read our blog. We are posting lots of things on our blog, and our latest story is about the Bugatti and its recent maiden voyage. And finally, we are also on Facebook. You can connect with us there. We post lots of tips and things on Facebook as well. Just go look for DynaVibe. And again, you can visit the website, send us email, sales@rpxtech.com. We appreciate your attention and attendance today. And if there's something we can do to help you out, please let us know. Thanks, everybody, and have a great day.